In the last two videos, I've covered two ways of evaluating a simple linear regression model using the regression standard error S and using the coefficient of determination R squared. In this video, I'm going to consider the third way of evaluating the fit of a simple linear regression model numerically, and that's by testing the slope parameter B1 or by calculating a confidence interval for the slope parameter. So let's think about what we're doing here when we're trying to infer about the slope parameter. As is the case in statistics and hypothesis testing, we are trying to infer about a population using a sample. And so in this figure here, I'm illustrating a hypothetical population. So that's what all these points are in this scatter plot. And it's just a generic example with a response variable y and a predictor variable x. And I've got a hypothetical population regression line here. That's the dashed line. And the equation of that is given by expected value of y is b0 plus b1x. And then all the individual points, they're a distance of e away from the line, e representing the random error for each point. And so each point can be represented as y equals b0 plus b1x plus e. So I'm imagining now that I am taking a random sample of 5 from this population. So these are the filled in points here. And then I'm estimating a simple linear regression model and using that to produce this regression line here, which is the solid line. So the question is, what does that sample regression line tell me about the population regression line? So I know what the sample regression line is. I can calculate its intercept and its slope, and I can plot it on a graph. But what I'm really interested in is, what does that tell me about the hypothetical population regression line? So if we think back to when we did a hypothesis test in the first chapter, we were looking to estimate the mean for some univariate data. And we did that by calculating a t-statistic, which was the sample mean, my, and we subtract the hypothesized mean, e of y, so this is the value that's in the null hypothesis, and then we divide by standard deviation divided by square root of n, and we call this the standard error of the estimate. And this test statistic under the null hypothesis has a t-distribution with n-1 degrees of freedom, n being the sample size. So it's very similar in this context. We calculate the t-statistic again, and it has the same general form. So the form of this is estimate minus hypothesized value divided by standard error. So estimate, b1 hat, that's the estimated slope, minus b1, the hypothesized value, divided by the standard error of the slope. So that's what this S b1 hat is. That represents a standard error of the slope. And under the null hypothesis, that has a t-distribution, just like it did in chapter 1, but now our degrees of freedom is not n-1, it's n-2. And a few videos ago I talked about where this 2 comes from, and it's because we're estimating 2 parameters in our model, the intercept and the slope. So let's run through an example, and we'll use our home prices example again. So our null hypothesis is that the slope is 0, versus the alternative hypothesis is that the slope is not 0. So we're doing a two-tail test here. What would it mean if the slope was 0? Well, then that would mean that there's no significant linear association between y and x. So what we're expecting here is that we're going to reject that null hypothesis in favor of the alternative, because everything we've done up to this point, it looks as if there is a linear association between sale price and floor size. So we calculate our t-statistic. So there's the formula here, and I've just repeated it here, and I've just plugged in the numbers that we've got from statistical software. So B1 hat, that's the slope estimate, 40.8. B1, that's the value in the null hypothesis, so 0. So I plugged in 0 here. And then SB1 hat, that's the standard error of the slope, so 5.684. So where am I getting that from? Well, if we look back at our R output in our coefficients table here, there's a lot of information, but the numbers that I'm interested in is the slope estimate, 40.8, B1 hat, and here's the standard error of that slope, 5.684. So that's S B1 hat. So that's the 5.684 here. And if I calculate this out, I get 7.18. And you'll see that the output down here also includes the result of that calculation. It's to 3 decimal places here, 7.179, but to 2 decimal places, 7.18. We're going to do the test at a significance level of 5%. And so we could do the test either using a critical value and seeing if our test statistic falls in the rejection region, or we could find the p-value and see if the p-value is smaller than our significance level. So the critical value, it's a t-distribution with n minus 2 degrees of freedom. So n is 5, 5 minus 2 is 3, so we're looking at a t-distribution with 3 degrees of freedom. We're doing a two-tail test. So we put half the significance level in one tail and half in the other tail. And so the percentile that we need to look at to get our critical value is going to be the 97.5th percentile, because it'll have 2.5% above it. And there'll be 2.5% in the other tail as well. So if we were to look at a table, we would find the 97.5th percentile of a t-distribution with 3 degrees of freedom is 3.182. Or we could find it using software. For example, using R, if I put 0.975, 3 degrees of freedom, using the QT function, that gives me my critical value there, 3.182. If I'm trying to find the p-value, then I need to look up a few more percentiles to try and narrow it down. So for example, let's see, the 99.5th percentile is 5.841. The 99.9th percentile is 10.214. So my test statistic, 7.18, is in between the 99.5th percentile and the 99.9th percentile. So the 99.5th percentile has an upper tail area of 0.005. So if I multiply that by 2, because we're doing a two-tail test here, I'm going to get 0.01. And then the 99.9th percentile has an upper tail area of 0.001. If I multiply that by 2, I get 0.002. So my p-value must be in between 0.01 and 0.002. Okay, now I can make my decision, because I can see that my test statistic is in the rejection region. It's above my critical value of 3.182. Or alternatively, I can see that if my p-value is bounded between 0.01 and 0.002, it's certainly less than 0.05, the significance level. And so I reject the null hypothesis in favor of the alternative hypothesis. In other words, the sample data favor a non-zero slope. That's what the alternative hypothesis says, that B1 is not equal to 0 at a significance level of 5%. So this is a way of evaluating the model because it tells me I've got a significant evidence of a non-zero slope here. So that's how to do a two-tail test with this significance level. How would things change if I was to do an upper tail test using that same significance level? So suppose I came into this thinking that there's probably a positive linear relationship between sale price and floor size. So I'm going to do an upper tail test. Well, the test statistic is the same. Significance level is the same. Critical value now, because I'm doing an upper tail test, I want the 95th percentile of that t-distribution. So that's 2.353. These percentiles are the same as before, but now I'm not going to multiply the tail areas by 2 to narrow down where my p-value is. I can just take them as given because I'm just operating in the upper tail, as this is an upper tail test. So my p-value must be in between 0.005 and 0.001. My decision is going to be, since the test statistic is above the critical value of 2.353, I reject the null in favor of the alternative, or equivalently, because the p-value is less than the significance level, I've bounded it between 0.005 and 0.001, so it's certainly less than 0.05. So now my conclusion is that the sample data favor a positive slope at a significance level of 5%, because my alternative hypothesis now, because I'm doing an upper tail test, is that B1 is greater than 0. Here's an illustration of what's going on here. So I've plotted my data as before. Here's my regression line, the solid dark line. And then these lighter gray colored lines, these are what the regression line would look like if in my population I really did have a 0 slope. So the way that I created this graph was to do a random sample of size 5 from a population where there was no relationship between y and x, and then I plotted the line, and then I took another sample and plotted the line again. And so these gray lines, if you like, give you a null distribution of regression lines. And because our sample regression line, this dark one, is well outside that distribution, this is evidence that I should reject the possibility of a null distribution here. I'm getting something that's very extreme, looks very unlikely to have occurred if that null distribution was true, and so I reject the null in favor of the alternative. I've got significant evidence of a non-zero slope here. One final thing before we move on to talk about confidence intervals is we can see in this computer output up here, I've got my B1 hat, I've got my standard error, I've got my test statistic. In this final column, it actually tells me the p-value. That's what this column gives me, is the p-value. It's repeated down here in my R output. And this is a two-tail p-value. And so before, when we did our calculations, we estimated that the p-value was in between 0.01 and 0.002. Well, in fact, it's 0.006 if you let computer software calculate it exactly. So that's a hypothesis test for the slope. When we covered hypothesis tests and confidence intervals in chapter 1, we talked about them being two sides of the same coin. So we can also look at this from the perspective of a confidence interval for the slope. So for example, a 95% confidence interval. I'm going to use the 97.5th percentile of the t-distribution with 3 degrees of freedom because I want 95% confidence. So that means if I was to have 2.5% in each tail, I would have 95% in the middle. And so the percentile that I need has to be the percentile that has 2.5% in the upper tail. So that's why there's a 97.5th percentile here. So now I can just calculate this out. It's the usual format for the confidence interval: estimate plus or minus t percentile times standard error. Here's my estimated slope, 40.8. Here's my t percentile, 3.182. And 5.684, that was the standard error for the slope. And then if I calculate this all out, I get this interval here, 22.7 up to 58.9. So loosely speaking, I could say that based on this data set, we're 95% confident that the population slope, B1, is between 22.7 and 58.9. If I want a more precise interpretation, I have to invoke the notion of repeated sampling and sampling distributions. So what that means is if we were to take a large number of random samples of size 5 from our population of homes, calculate a 95% confidence interval each time, then 95% of those confidence intervals would contain the unknown population slope. So this is the technical statistical definition of a confidence interval, but this one here, this interpretation here, this looser one, this is the one that's going to be a little more understandable to people and not quite as wordy. How would this change if we were to calculate a 90% confidence interval instead of a 95% confidence interval? Well, if we look at our formula, this piece will be the same because the center of the interval will be the same, centered at the estimate. This piece will be the same, the standard error is the same. The only bit that would change is the percentile. So if we need to use a 97.5th percentile for a 95% interval, for a 90% interval, we're going to have to put 5% in each tail to have 90% left over in the middle, and so we need the 95th percentile. So if we go back to the calculations we did on the side, there's the 95th percentile, 2.353. So here if we do 40.8 plus or minus 2.353 times 5.684, if we calculate that out, then we get 27.4 up to 54.2. So that would be a 90% confidence interval. And let me just show you how to do all this in R. So here's the calculations for the 95% confidence interval. There's the 97.5th percentile. There's that 97.5th percentile times the standard error, comes to 18.086. And then if I do 40.8 plus or minus 18.086, I get 22.7 up to 58.9. We can also use this confint function to get the interval directly. So here it is here, 22.7 up to 58.9. Here's the calculations for the 90% confidence interval. There's the percentile. There's the value of the number if we multiply that percentile times the standard error. And then if we do 40.8 plus or minus that number, we get 27.4 up to 54.2. And then if we run that confint function with argument level equal 0.9, we get the 90% confidence interval right there, 27.4 up to 54.2. So that's how to evaluate the fit of a simple linear regression model by considering the slope. So now we've talked about 3 different ways of evaluating the fit of a simple linear regression model numerically, using the regression standard error S, the coefficient of determination R squared, and thinking about the slope B1.